Hey guys, and welcome back to Quantic Academy. So today we will be talking about integration. Now, what is integration? To put simply, integration is basically the direct opposite of differentiation. Okay? So that means if you have a function f of x and you differentiate it, you get something like f prime of x. But if you want to get f of x again, then you integrate it. So it's like the opposite of differentiation. So it's like plus and minus, multiply and divide. So they're opposites, okay? So if you have a function f of x and you want to integrate it, then it'll be the same thing as finding the antiderivative. Now, I'm going to call the antiderivative capital F of x. And this is such that when you differentiate this, you get back f of x, okay? So capital F of x is the antiderivative, or the integral of lowercase f of x, okay? So that's what integration is. But you probably heard of integration corresponding to area under the curve. So I'm going to explain to you how integration relates to area under the curve. Well, think of a distance time graph. Velocity speed time graph, okay? You know the area under a speed time graph corresponds to the distance traveled, right? You probably heard of that. If you're unfamiliar with that concept, let me illustrate it to you. So let's say I have a speed time graph. I'm going at 5 meters per second. And let's say I'm going for 10 seconds, okay? So 10 seconds here, okay. Now, what's the distance traveled? Well, if I move 5 meters per second for 10 seconds, that's 50 meters per second. 5 times 10, okay? So that's 50 meters per second. Now, what's the area under the graph? It'll just be the area under this rectangle from 0 to 10, because I'm stopping at time 10. I'm traveling for 10 seconds, okay? The area under the graph will be the area of this rectangle. The height is 5, and the width is 10. So the area is 50. The area is 50. Oh, that's the same thing as the distance traveled. So the distance traveled is related to the area, okay? The distance, I'm just going to use something like this to say they're related. Okay, or actually, like this to say they're related, okay? The distance traveled is related to area. Now, distance traveled is also related to the change in position. It's related to the change in position. Now, why is that? Well, if I'm at the 10 meter mark, and then later I'm at the 2 meter mark, then I've traveled 8 meters, 10 minus 2, the change in position, okay? Now, what do we know about velocity? We know velocity is change in position. I'm going to use x for position over time, or change in time. So if I have a position time graph now, or distance time graph, let's say distance, let's just say position time graph, and it looks something like this, for example, then the velocity is a change in x over change in t. That'll just be the gradient, because here the x represents the y value, because position represents the y, and time represents the x. So it'll be change in y over change in x. That's just the gradient. The velocity is the gradient. And if you watch our other video on differentiation, then you know the gradient is equal to the derivative. So the velocity is just the derivative of the position. So velocity is the derivative of the position. That means the position is the antiderivative of the velocity. Because if you differentiate the position, you get velocity. So that means when you integrate the velocity, you get the position. Okay? And we know that change in position is the same thing as distance traveled. So now you can see how distance traveled relates to antiderivative, and how an area, because the distance traveled is the area under the curve. So now you can see how the area under the curve relates to the antiderivative. Okay? So this is just an analogy. It's not a formal proof. If you want to see a formal proof, then you can search up the fundamental theorem of calculus, Or you can leave a comment and I will make a video on it in the future. Okay. So integration is the area under the curve. Now we see how they relate. Okay. So how would you actually find the area under the curve? What does it mean? Well, firstly, if I have a function, then the area under the curve, first I need to draw two lines because the function is infinitely long. So I need to find a region first. So I'll draw two lines to denote a region. And the area under the graph would be this shaded area here. Okay. Now how would I actually find that? Well, suppose I have a random function. I'll call it f of x. Okay. And let's say it looks something like this. Okay. So now I want to find the area under the graph. I'll separate the region out with this line. So I can approximate the area. So the thing is, this is curved, and we can't really use geometry here. We can't use pi r squared or something like that, because it's not really a curve that we can use geometry for. It's not a circle, it's nothing like that. So what we can do is we can approximate the area. We can approximate the area by using rectangles. So if I use a rectangle here and a rectangle here, I can get a good approximate for the area. However, there is still some error here, you know. If I find the area of these rectangles and add them together, I'm missing out this area, but I'm also adding an extra bit here, which is not under the graph. This is above the graph. This is not the area we want. So I have some error, okay? If I use some rectangles to approximate it, I have some error. So what can I do? Well, I can try to reduce the error because I want an accurate answer. So if I reduce the error, what I can do is I can reduce the width of the rectangle, okay? So this is the width of the rectangle. I can reduce it, and what I'll do, if I draw, so let me draw a smaller version here. If I make the width smaller, then as you can see, the error here is much smaller, okay? The error here is much smaller. And so, the smaller the width of the rectangles, the lower the error. So that means we want small rectangles. So how do we make the width smaller? Well, we can add more rectangles. Because if we add more rectangles in the same length, it's the same space, right? So if we add more rectangles, then the width of each one will be smaller. Okay, so we can add more rectangles. So if I add more rectangles, then the error will be lower, and the area of the rectangles will be closer to the actual area under the curve. So now I made a rectangle smaller by adding more rectangles. As you can see, the error is much lower. But even though error is lower, this is still there. Okay. Now adding more rectangles reduces the error. So if I add infinitely many rectangles, then there'll be no error at all. And then it would be the exact same as the area under the graph. I cannot add infinitely many rectangles. That makes no sense. So what we do is we say we're taking the limit. So we're taking the limit. Okay, we're taking the limit. And this is a method in calculus. Because in calculus, we deal with infinitely small things. Actually, we don't deal with infinitely many small things. We dissect something into infinitely many small things. And then we build it up from there. And since we can't deal with infinities directly, we do something what we call taking the limit. Okay? So we're going to have infinitely many rectangles. Now I'm going to draw another graph here. I'm going to draw another diagram here. But for the sake of illustration purposes, I can't draw infinitely many rectangles. So I'll just approximate it like this. Okay, and these dot dots just represent more rectangles. Okay. So there's still error here because I didn't draw it infinitely small. But if you draw it infinitely small, then there'll be no error at all. And then the area of all these rectangles will be the exact same as the area under the graph. Now, what's the area of each of these rectangles? well, what's the width? So the width would be the change in x, okay? That'll be delta x. But if I make delta x infinitely small, then what do we get? Then we call that dx. So dx is basically when delta x is infinitely small. It's a tiny, 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 tiny change in x, okay? So that'll be the width. What's the height? Well, I made it so that the rectangles touch the graph, okay? So the height would just be the value of the graph at that point. It would be f of x. Okay, so the area of the rectangle, of each rectangle, is f of x. And the area of all the rectangles, hence the area under the curve, would be the sum of all f of x times dx, sum of all the tiny little areas. And we use this is the integral sign, and it looks like a long S to represent sum. Okay. So the area under the curve is an infinite sum. Area under the curve is an infinite sum, basically. Okay? And we're integrating it from A to B. We're finding the sum from A to B. These are the bounds. Okay, so that's the interval in which we're calculating the area under. And as we showed before, the area under the curve is equal to the antiderivative. But more specifically, it's actually the change in antiderivative. So this capital F of x represents the antiderivative. And this notation that I wrote here, that just means the change in antiderivative. So it'll be evaluated at B minus evaluated at A. And this change in antiderivative gives the area under the curve. So now you see how integration is linked to area under the curve, and how integration is linked to infinite sums. So that's basically what integration is. Integration is just an infinite summation. Thank you guys for watching. Hope you enjoyed it. If you did, leave a like, and see you guys next time. Goodbye.